Understanding Electronics Part, MCU, 6 for Hobby Electronics Club. Understanding Electronics Part, MCU, 6 for Hobby Electronics Club, by P. Ram. Introduction. Black Mall Square, we learned microcontroller classification in terms of bits in previous episodes. Black Mall Square, we learned about 8, 16-bit, and 32-bit microcontrollers. In our previous episodes, Black Mall Square, we learned about 64-bit microcontroller and their family in last episode. Black Mall Square, we will learn Silica-Carbide, Gallium Nitrate technology in this episode. Black Mall Square, we will learn about advantage of this new technologies. SiC equals Silica-Carbide. GaN equals Gallium Nitrate. C equals silica. Introduction. Black Mall Square, this episode highlights the benefits of using SiC and GaN-based WBG semiconductors. Black Mall Square reviews the current state-of-the-art devices and solutions. Black Mall Square shows how SiC and GaN can be a strong and viable candidate for future power electronics and systems applications. WBG equals wide band gap. Steps in semiconductor manufacturing. Semiconductor manufacturing utilizes a combination of photolithography, etching, deposition, and doping processes, along with specialized equipment to create complex electronic circuits on silicon wafers. These processes are highly precise and require advanced equipment and clean room environments. Steps. 1. Wafer fabrication. 2. Deposition. 3. Photolithography. 4. Etching. 5. Doping. 6. Advanced techniques. 1. Wafer fabrication. Black Mall Square semiconductor devices start with highly pure silicon ingots, which are then sliced into thin wafers. Black Mall Square, these wafers are polished to a smooth surface and then undergo various deposition processes to create layers of different materials. 2. Deposition. Black Mall Square, various techniques are used to deposit thin films onto the wafer, including physical vapor deposition, PVD, chemical vapor deposition, CVD, and atomic layer deposition, ALD. To Black Mall Square, these processes create the foundation for circuits, transistors, and other components. 3. Photolithography. Black Mall Square, this process uses light and photoresist to create patterns on the wafer, defining the features of the circuit. Black Mall Square photomask is used to project the desired pattern onto the photoresist, which is then developed to create a mask for subsequent etching. 4. Etching. Black Mall Square etching is used to remove unwanted material from the wafer, exposing the desired features defined by the photolithography process. Black Mall Square, both wet and dry etching techniques are employed, with dry etching using gases to precisely define the patterns. 5. Doping. Black Mall Square, doping introduces impurities into the semiconductor material to alter its electrical properties, enabling the creation of transistors and other devices. Black Mall Square, this process involves diffusing dopants like boron or phosphorus into the wafer to create specific electrical regions. 6. Advanced techniques. Black Mall Square modern semiconductor manufacturing relies on advanced techniques like advanced etch technology and double, quadruple, and spacer-based patterning to create increasingly smaller and more complex features. Black Mall Square, these techniques enable the creation of high-performance chips with enhanced capabilities. Semiconductor wafers. Black Mall Square semiconductor wafers come in various types, primarily classified by material and doping. The most common materials are silicon, germanium, and gallium arsenide, with silicon being the most widely used due to its availability and versatility. Wafers are also classified as undoped, doped or with different crystal orientations like 100 or 111. Types of wafers. 1.By material use, 2.By doping, 3.By orientation, 4.Other types. Classification of wafers by material. Silicon Si. Black small square, the most prevalent material, used in a wide range of applications, including integrated circuits, microprocessors, and solar cells. Germanium Ge. Black Mall square used in high-frequency transistors, infrared detectors, and other optical devices. Gallium arsenide, GaAs. Black small square ideal for high-speed transistors, solar cells, and other applications requiring high efficiency. Indium phosphide, InP. Black small square used for optoelectronic applications, fast transistors, and resonance tunneling diodes. Classification of wafers by material. Gallium nitride, GaN. Black small square used in power electronics, LEDs, and high-frequency applications. Black small square silicon carbide. SiC black small square used in power electronics, high-frequency devices, and high-temperature applications. Compound semiconductors. Black small square, these materials are made from combinations of elements, like gallium arsenide, GaAs, and are used in various fields, including photovoltaics and microelectronics. By doping. Undoped. Black small square, also known as intrinsic, these wafers have a minimal concentration of impurities and are used as a base material for further processing. Doped. Black small square, these wafers are intentionally doped with impurities to alter their electrical conductivity, creating P-type or N-type wafers. Black small square P-type, doped with elements like boron, creating a surplus of holes. Positive charge carriers. Black small square N-type, doped with elements like phosphorus, arsenic, or antimony, creating a surplus of electrons. Negative charge carriers. 3. By crystal orientation. 100. Black small square, commonly used in manufacturing due to its good etching and lithographic properties. 111. Black small square used in specific applications where it provides unique properties for device fabrication. 110. Black small square, less common than 100 or 111, but used in some specialized applications. Key aspects of Miller indices. Black small square, the integers denote the inverse of the intercepts the crystal plane makes with the x, y, and z-axis. Black small square, the plane with Miller indices 100, is parallel to the x-axis, plane 0, 10, is parallel to the y-axis, and so on. Black small square low index planes like 100, 110, and 111 are important in describing silicon wafer orientation. Black small square Miller indices planes. Miller indices. Miller indices provide a standardized way to specify directions and planes in the crystal. Structure. Knowing the Miller index is crucial for understanding wafer orientation. 19. TGS Private Limited for HC. Other types. Silicon on insulator, SI. Black small square, a wafer structure with a thin layer of silicon on top of an insulating layer, such as silicon dioxide, offering improved performance and power efficiency. Black small square fused silica/quartz wafers. Black small square used in various applications where high thermal resistance, low thermal expansion, and UV transparency are required. Sapphire, Al203. Black small square used as a substrate for GaN LEDs due to its high thermal conductivity and transparency. MEMS wafers. Black small square wafers designed for microelectromechanical systems, MEMS, which are used in sensors and actuators. Definitions. Valence band. Black small square, this band contains electrons that are tightly bound to atoms and involved in bonding. Conduction band. Black small square, this band contains electrons that are free to move and participate in electrical conduction. Band gap. Black small square, the energy difference between the valence and conduction bands. This is the forbidden energy range where electrons cannot exist in the semiconductor. Energy required for conduction. Black small square, to conduct electricity, electrons must have enough energy to jump from the valence band to the conduction band. This is the energy required to overcome the band gap. Semiconductor properties. The size of the band gap influences a semiconductor's conductivity, optical properties, and ability to be used in various electronic devices. Black small square, large band gaps. Materials with large band gaps, like wide bandgap semiconductors, are good insulators because it takes a lot of energy to excite electrons. Black small square, small band gaps. Materials with small band gaps, like some narrow bandgap semiconductors, are good conductors because electrons can easily jump to the conduction band. Definition of band gap. The difference in energy between the valence band and the conduction band is called an energy gap or band gap. This is the amount of energy that a valence electron must have in order to jump from the valence band to the conduction band. Once in the conduction band, the electron is free to move throughout the material and is not tied to any given atom. The band gap is illustrated. Band gap is illustrated. Black small square, the band gap, is illustrated in Figure 1, A, for insulators. In semiconductors, the band gap is smaller, allowing an electron in the valence band to jump into the conduction band if it absorbs a photon. Black small square, the band gap, depends on the semiconductor material. This is illustrated in Figure 1. B, black small square in conductors. The conduction band and valence band overlap, so there is no gap, as shown in Figure 1. C. This means that electrons in the valence band move freely into the conduction band, so there are always electrons available as free electrons. Silicon-based semiconductor. Silicon-based semiconductors, black small square silicon-based semiconductors are materials, primarily silicon, that have an electrical conductivity between that of a conductor and an insulator. Black small square, they are widely used in electronic devices like transistors, integrated circuits, and solar cells. Black small square, the band gap of silicon, which is the energy difference between the top of the valence band and the bottom of the conduction band, is approximately 1.12 electron volts eV. Silicon as a semiconductor. Black small square silicon is a group 4 element in the periodic table. Black small squared is a semiconductor because its electrical conductivity can be altered by introducing impurities, doping, or applying external fields. Black small square, this allows it to be used in a wide variety of electronic applications where conductivity needs to be controlled. Purpose of doping. Black small square, doping in silicon semiconductors involves adding controlled amounts of impurities to alter its electrical conductivity. Black small square, this process is crucial for making semiconductors useful in electronics, as it transforms them from mediocre conductors into materials with specific desired properties. Black small square, there are two main types of doping, N-type and P-type. N-type doping. Black small square, this involves adding elements with 5 valence electrons, pentavalent impurities, to silicon. Black small square examples of N-type dopants include phosphorus, P, arsenic, As, and antimony, Sb. Black small square, when these dopants are added, they form bonds with 4 surrounding silicon atoms, leaving 1 extra electron that can move freely, increasing the number of charge carriers and enhancing conductivity. P-type doping. Black small square, this involves adding elements with 3 valence electrons, trivalent impurities, to silicon. Black small square examples of P-type dopants include boron, B, and gallium, Ga. Black small square, when these dopants are added, they form bonds with 3 surrounding silicon atoms, creating a hole or an electron deficiency that can accept electrons from neighboring bonds, increasing the number of charge carriers, holes, and enhancing conductivity. Doping methods. Black-Small-Square diffusion. Black-Small-Square heating the silicon wafer in a controlled atmosphere containing the dopant gas. Black-Small-Square ion implantation. Black-Small-Square using an accelerated beam of dopant ions to implant them into the silicon crystal lattice. Common doping impurities. Black-Small-Square phosphorus, P for N-type doping. Black-Small-Square boron, B for P-type doping. Black-Small-Square arsenic, S for N-type doping. Black-Small-Square antimony, Sb for N-type doping. Black-Small-Square gallium, Ga for P-type doping. Black-Small-Square indium, In for P-type doping. Black-Small-Square aluminum, Al for P-type doping. Silica crystal structure with impurity. Silica pure crystal atomic arrangement. Crystal after doping phosphorus. Effect of doping. Band gap. Silicon carbide wafer. Silicon-based semiconductor. Silicon carbide, SiC, semiconductor. Black-Small-Square silicon carbide, SiC, based semiconductor is a compound semiconductor made from silicon and carbon. Black-Small-Square is known for being a wide bandgap material, meaning it can withstand higher voltages and operate at higher temperatures than traditional silicon semiconductors. Black-Small-Square, this makes it suitable for high-power electronics, optoelectronics, and high-temperature applications. How is silicon carbide made? 1. Lely method. 2. Chemical vapor deposition. Lely method. Black-Small-Square, the simplest silicon carbide manufacturing method, involves melting silica sand and carbon, such as coal, at high temperatures up to 2,500 degrees Celsius. Darker, more common versions of silicon carbide often include iron and carbon impurities, but pure SiC crystals are colorless and form when silicon carbide sublimes at 2,700 degrees Celsius. Once heated, these crystals deposit onto graphite at a cooler temperature in a process known as the Lely method. Black-Small-Square, during this process, a granite crucible heats to a very high temperature, usually by way of induction, to sublimate silicon carbide powder. A graphite rod with lower temperature suspends in the gaseous mixture, which inherently allows the pure silicon carbide to deposit and form crystals. Chemical vapor deposition. Black-Small-Square, alternatively, manufacturers grow cubic SiC using chemical vapor deposition, which is commonly used in carbon-based synthesis processes and used in the semiconductor industry. In this method, a specialized chemical blend of gases enters a vacuum environment and combines before depositing onto a substrate. Note: Black-Small-Square, both methods of silicon carbide wafer production require vast amounts of energy, equipment, and knowledge to be successful. SiC wafer creation. Black-Small-Square SiC wafers are produced from single crystals of silicon carbide, typically grown using methods like the Lely method or chemical vapor deposition, CVD, according to Arrow Electronics. These crystals are then cut into thin wafers using saws or lasers. Crystal structure of SiC. Chip fabrication. Black-Small-Square pattern transfer. Photolithography is used to create intricate patterns on the wafer surface using light and chemicals. Black-Small-Square doping. The wafer is bombarded with specific ions to alter its electrical conductivity, creating regions with different properties. Black-Small-Square deposition. Layers of different materials are deposited on the wafer to create insulation, wiring, and other necessary structures. Black-Small-Square etching. Unwanted materials are removed from the wafer using chemical or physical etching processes, revealing the design circuits. Chip dicing and packaging. Black-Small-Square, these circuits are fabricated on the wafer. Black-Small-Square, the wafer is cut into individual chips using a dicing saw or laser. Black-Small-Square, these chips are then packaged for use in electronic devices. After measures for protection and connections to external circuitry. A MOSFET using SiC technology. Key characteristics of SiC semiconductors. Wide band gap. Black small square, the band gap of SiC is significantly larger than that of silicon, allowing it to withstand higher voltages and operate at higher temperatures. High thermal conductivity. Black small square SiC has a high thermal conductivity, which helps dissipate heat generated during operation, improving reliability. High breakdown voltage. Black small square SiC can withstand significantly higher breakdown voltages than silicon, making it ideal for high power applications. High electron mobility. Black small square SiC offers higher electron mobility, which can lead to faster switching speeds in electronic devices. Applications of SiC semiconductors. Power electronics. Black small square SiC semiconductors are used in power converters, inverters, and motor drives in applications like electric vehicles, renewable energy systems, and industrial automation. High temperature electronics. Black small square SiC devices can operate at high temperatures, making them suitable for applications like aerospace, automotive, and oil and gas extraction. Optoelectronics. Black small square SiC is used in LEDs, photodetectors, and other optical devices. RF devices. Black small square SiC transistors can be used in high-frequency applications, such as in wireless communication and radar systems. Manufacturing SiC semiconductors. Black small square SiC wafers are typically grown from single crystals using techniques like the Lely method, which involves sublimating silicon carbide powder and depositing it onto a graphite substrate. Black small square these wafers are then processed to create various CC-based devices. Impurities for doping. Black small square impurities in SiC semiconductors are elements that affect its electrical properties, such as N-type or P-type doping. Black small square, commonly nitrogen and phosphorus, are used for N-type, doping black small square aluminum. Boron and gallium are used for P-type doping. Black small square other elements like free C, SiO2, Fe, T, Al, Ni, and V can also be present as impurities, although their presence is typically minimized. Elaboration. Doping for semiconductor behavior. Black small square SiC can behave as a semiconductor when impurities or dopants are added. Black small square N-type doping. Black small square nitrogen and phosphorus are commonly used to create N-type semiconductors, where electrons are the majority charge carriers. Black small square P-type doping. Black small square aluminum, boron, and gallium are commonly used to create P-type semiconductors, where holes are the majority charge carriers. Black small square other impurities. Black small square, while the primary goal is to control doping, other impurities like SiO2, free C, Fe, T, Al, Ni, and V can be present, especially in technical SiC. Impact of impurities. Black small square, the type and concentration of impurities can significantly affect the electrical characteristics of SiC, impacting its performance in electronic devices. Application is SiC technology. Black small square SiC has become a key player in the semiconductor industry, powering MOSFETs, Schottky diodes, and power modules for use in high-power, high-efficiency applications. While more expensive than silicon MOSFETs, which are typically limited to breakdown voltages at 900 V, SiC allows for voltage thresholds at nearly 10 kV. Black small square SiC also has very low switching losses and can support high operating frequencies, which allows it to achieve currently unbeatable efficiencies, especially in applications that operate at over 600 volts. With proper implementation, SiC devices can reduce converter and inverter system losses by nearly 50%, size by 300%, and overall system cost by 20%. This reduction in overall system size lends SiC the ability to be extremely useful in weight and space-sensitive applications. Gallium